To bring out a definitive volume, teaching the art of the subject. By art we meant the kind of mastery that comes from an intimate familiarity with real circuits, actual devices, and the like, rather than the more abstract approach often favored in textbooks on electronics. Of course, in a rapidly evolving field such as nuts and bolts approach has its hazards, most notably a frighteningly quick obsolescence. The pace of electronics technology did not disappoint us. Hardly was the ink dry on the first edition before we felt foolish reading our words about the classic 2 kilobyte 2716 EPROM with a price tag of about $25. They're so classic you can't even get them anymore, having been replaced by the EPROM 64 times less large and costing less than half the price. Thus, a major element of this revision responds to improved devices and methods, completely rewritten chapters on microcomputers and microprocessors using the IBM PC and the 68008, and substantially revised chapters on digital electronics, including PLDs and the new age C and AC logic families, on op-amps and precision design, reflecting the availability of excellent fed input op-amps, and on construction techniques, including CAD/CM. Every table has been revised, some substantially. For example, in Table 4.1, operational amplifiers, only 65% of the original 120 entries survived, with 135 new op-amps added. We have used this opportunity to respond to readers suggesting to our own experiences using and teaching from the first edition. Thus, we have rewritten this chapter on FET. It was too complicated and repositioned it before the chapter on op-amps, which are increasingly of FET construction. We have added a new chapter on low power and micro power design, both analog and digital, a field both important and neglected. Most of the remaining chapters have been extensively revised. We have added many new tables, including AD and DA converters, digital logic components, and low power devices, and throughout the book we have expanded the number of figures. The book now contains 78 tables, available separately as the Horowitz and Hill components selection tables, and over 1,000 figures. Throughout the revision we have strived to retain the feeling of informality and easy access that made the first edition so successful and popular, both as reference and text. We are aware of the difficulty students often experience when approaching electronics for the first time. The field is densely interwoven, and there is no path of learning that takes you by logical steps from neophyte to broadly competent designer. Thus we have added extensive cross-referencing throughout the text. In addition, we have expanded the separate laboratory manual into a student manual for the art of electronics, by codes, complete with additional worked examples of circuit designs, explanatory material, reading assignments, laboratory exercises, and solutions to selected problems. By offering a student supplement, we have been able to keep this volume concise and rich with detail, as requested by our many readers who use the volume primarily as a reference work. We hope this new edition responds to all our readers' needs. Both students and practicing engineers welcome suggestions and corrections, which should be addressed directly to Coates, Harvard University at Cambridge MA 02138. In preparing this new edition, we are appreciative of the help we received from a lot of people and colleagues. Legal notice. In this book we have attempted to teach the techniques of electronic design using circuit examples and data that we believe to be accurate. However, the examples, data and other information are intended solely as teaching aids and should not be used in any particular application without independent testing and verification by the person making the application Independent testing and verification are especially important in any application in which incorrect functioning could result in personal injury or damage to property. For these reasons, we make no warranties express or imply that the examples, data, or other information in this volume are free of error, that they are consistent with industry standards, and that they will meet the requirements for any particular application. The authors and publisher expressly disclaim the implied warranties of merchantability and of fitness for any particular purpose. Even if the authors have been advised of a particular purpose, and even if a particular purpose is indicated in the book, the authors and publisher also disclaim all liability for direct, indirect, incidental, or consequential damages that result from any use of the examples, data, or other information in this book. Preface to the third edition. Moore's law continues to assert itself, unabated, since the publication of the second edition a quarter century ago. In this new third and final edition, we have responded to this upheaval with major enhancements, an emphasis on devices and circuits from AD to D and DA conversion. Chapter 13. Because embedded microcontrollers are everywhere, illustration of specialized peripheral ICs for use with microcontrollers. Chapter 15. Detailed discussions of logic family choices and of interfacing logic signals to the real world. Chapter 10 and 12. Greatly expanded treatment of important topics in the essential analog portion of instrument design. Precision circuit design, Chapter 5. Low noise design, Chapter 8. Power switching, Chapter 3, 9, and 12. Power conversion, Chapter 9. And we have added many entirely new topics, including digital audio and video, including cable and satellite TV, transmission lines, circuit simulation with SPICE, impedance amplifiers, depletion mode, MOSFETs, protected MOSFETs, high side drivers, quartz crystal properties and oscillators, a full exploration of JFETs, high voltage regulators, optoelectronics, power logic resistors, delta sigma converters, precision multi-slope conversion, memory technologies, cellular buses, illustrative design by the masters. In this new edition, we have responded also to the reality that previous editions have been enthusiastically embraced by the community of practicing circuit designers. Even though the art of electronics, now 35 years in print, originated as a course textbook, so we continued the how we do it approach to circuit design, and we've expanded the depth of treatment while we hope retaining the easy access and explanation of basics. At the same time, we have split off some of the specifically course-related teaching and lab material into separate Learning the Art of Electronics volume, a substantial expansion of the previous edition's companion student manual for the art of electronics. Digital oscilloscopes may have made it easy to capture, annotate, and combine measured waveforms, a capability we have exploited by including some 90s scope screenshots illustrating the behavior of working circuits. Along with those doses of reality, we have included in tables and graphs substantial quantities of highly useful measured data, such as transistor noise and gain characteristics, analog switch characteristics, capacitance, op-amp input and output characteristics, over frequency input common mode range, output swing, auto zero recovery, distortion, available packages, and approximate prices, ! The sort of data often buried or omitted in data sheets, but which you need and don't have the time to measure. When designing circuits, we've worked diligently over the 20 years it has taken to prepare this edition, to include important circuit design information in the form of some 350 graphs, 50 photographs, and 87 tables, listing more than 1,900 active components. The last enabling intelligent choice of circuit components by listing essential characteristics, both specified and measured, of available parts. Because of the significant expansion of topics and depth of detail, we've had to leave behind some topics that were treated in a second edition, notwithstanding the use of larger pages, more compact fonts, and more figure-sized to fit in a single column. Some additional related material that we had hoped to include in this volume on real-world properties of components and advanced topics in BGTs, FETs, op-amps, and power control will instead be published in a forthcoming companion volume, The Art of Electronics, the X chapters. References in this volume to those X chapters sections and figures are set in italics. A newly updated Art of Electronics.com website will provide the home for continuation of the previous editions, collections of circuit IDs and bad circuits. It is our hope that it will become a community also for a lively electronic circuit forum. As always, we welcome corrections and suggestions, and of course fan mail, which can be sent to horowitz@physics.harvard.edu or to hill@rowland@harvard.edu. With gratitude, where to start in thanking our invaluable colleagues. Legal notice addendum. In addition to the legal notice appended to the preface to the second edition, we also make no representation regarding whether or use of the examples, data, or other information in this volume might infringe others' intellectual property rights, including US and foreign patents. It is the reader's sole responsibility to ensure that he or she is not infringing any intellectual property rights, even for use which is considered to be experimental in nature. By using any of the examples, data, or information in this volume, the reader has agreed to assume all liability for any damages arising from or relating to such use, regardless of whether such liability is based on intellectual property or any other cause of action, and regardless of whether the damages are direct or indirect, incidental, consequential, or any other type of damage. The author and publisher disclaim any such liability. This page intentionally left blank. Foundations, Chapter 1, 1.1, Introduction. The field of electronics is one of the great success stories of the 20th century. From the crude spark gap transmitters and cat's whiskers detectors at its beginning, the first half century brought an era of vacuum tube electronics that developed considerable sophistication and found ready application in areas such as communications, navigation, and instrumentation control and computation. The latter half century brought solid-state electronics, first as discrete transistors, then as magnificent arrays of them within integrated circuits, ICs, and a flood of stunning advances that shows no sign of abating. Compact and inexpensive consumer products now routinely contain many millions of transistors, VLSI, very large-scale integration, chips, combined with elegant optoelectronics, displays, lasers, and so on. They can process sounds, images, and data, and for example permit wireless networking in the short packet, access to the pooled capabilities of the Internet. Perhaps as noteworthy is the pleasant trend toward increased performance per dollar. The cost of an electronic microcircuit routinely decreases to a fraction of its initial cost, as the manufacturing process is perfect. See figure 10.87. For an example, in fact, it is often the case that the panel, controls, and cabinet hardware of an instrument cost more than the electronics inside. On reading of these exciting new developments in electronics, you may get the impression that you should be able to construct powerful, elegant, yet inexpensive little gadgets to do almost any conceivable task. All you need to know is how all these miracle devices work. If you had that feeling, this book is for you. In it we have attempted to convey the excitement and know-how of the subject of electronics. In this chapter we begin the study of the laws, rules of thumb and tricks that constitute the art of electronics as we see it. It is necessary to begin at the beginning. We talk of voltage, current, power and the components that make up electronic circuits. Because you can't touch, see, smell or hear electricity, there will be a certain amount of abstraction, particularly in the first chapter, as well as some dependence on such visualization instruments as oscilloscopes, voltmeters. In many ways, the first chapter is also the most mathematical, in spite of our efforts to keep mathematics to a minimum in order to foster a good intuitive understanding of circuit design and behavior. In this new edition, we've included some intuition aiding approximations that our students have found helpful. And by introducing one or two active components ahead of their time, we are able to jump directly into some applications that are usually impossible in a traditional textbook. Passive electronics chapter. This will keep things interesting and even exciting. Once we have considered the foundations of electronics, we will quickly get into the active circuits, amplifiers, oscillators, logic circuits, etc. that make electronics the exciting field it is. The reader with some background in electronics may wish to skip over this chapter, since it assumes no prior knowledge of electronics. Further generalizations at this time would be pointless. So let's just dive right in. 1.2 voltage, current, resistance. 1.2.1 voltage and current. There are two quantities that we like to keep track of in electronic circuits, voltage and current. These are usually changing with time, otherwise nothing interesting is happening. Voltage is symbol V or sometimes E. Officially, the voltage between 2 points is the cost in energy, work done, required to move a unit of positive charge from the more negative point, lower potential, to the more positive point, higher potential. Equivalently is the energy released when a unit charge moves downhill from the higher potential to the lower. Voltage is also called potential difference or electromotive force, EMF. The unit of measure is the volt, with voltage usually expressed in volts. V, kilovolts, 1 kV is 10 to the power 3 V. Millivolts, 1 MV is 10 to the power minus 3 V. Or microvolts, 1 microvolt is 10 to the power minus 6 V. See the box on prefixes a joule, J. A work is done in moving a coulomb, C, of charge through a potential difference in 1 volt. V. The coulomb is the unit of electric charge, and it equals the charge of approximately 6 times 10 to the power 18 electrons, for reasons that will become clear later. The opportunities to talk about nanovolts. 1 nanovolt is 10 to the power minus 9 volts. Megavolts, 1 MV is 10 to the power 6 volts are rare. Current, symbol I. Current is the rate of flow of electric charge past the point. The unit of measure is the ampere or amp, with current usually expressed in amperes, A, milliamperes. 1 mA is minus 10 to the power minus 3 ampere. Microamperes is 1 microampere is 10 to the power minus 6 ampere. Nanoamperes, 1 nanoampere is 10 to the minus 9 ampere. Occasionally picoamperes, 1 PA is 10 to the power minus 12 amperes. A current of 1 amp equals a flow of 1 coulomb of charge per second. By convention, current in a circuit is considered to flow from a more positive point to a more negative point, even though the actual electron flow is in the opposite direction. Important. From these definitions you can see that currents flow through things and voltages are applied or appear across things. So you've got to say it right. Always refer to the voltage between 2 points or across 2 points in a circuit. Always refer to current through a device or connection in a circuit. To say something like the voltage through a resistor is nonsense. However, we do frequently speak of the voltage at a point in a circuit. This is always understood to mean the voltage between that point and ground. A common point in the circuit that everyone seems to know about, soon you will too. We generate voltages by doing work on charges in devices such as batteries, conversion of electrochemical energy, generators, conversion of mechanical energy by magnetic forces, solar cells, photovoltaic, conversion of the energy of photons, etc. We get currents by placing voltages across things. At this point you may well wonder how to see voltages and currents. The single most useful electronic instrument is the oscilloscope, which allows you to look at voltages, occasionally currents, in a circuit as a function of time. We will deal with oscilloscopes and also voltmeters when we discuss signals shortly. For a preview, see Appendix 0 or 0, see Appendix O and the multimeter box later in this chapter. In real circuits, we connect things together with wires and metallic conductors, each of which has the same voltage on it everywhere. With respect to ground, say, we mention this now so that you will realize that an actual circuit doesn't have to look like a schematic diagram, because the wires can be rearranged. Here are some simple rules about voltage and current. The sum of the currents into a point in a circuit equals the sum of the currents out of conversion of charge. This is something called Kirchhoff's current law, KCL. Engineers like to refer to such a point as a node. It follows that for a series circuit, a bunch of two-terminal things all connected end to end, the current is the same everywhere. 2.2. Things hooked in the parallel, figure 1.1, have the same voltage across them. Restate that the sum of the voltage drops from A to B via one path through a circuit equals the sum by any other route, and is simply the voltage between A and B. Another way to say it is that the sum of the voltage drops around any closed circuit is 0. This is Kirchhoff's voltage law, KVL. The power energy per unit term consumed by a circuit device is simply energy charge times charge divided by time. For volts, in volts and I in amps, P comes out in watts. A watt is the joule per second. 1 watt is 1 joule per second. So for example, the current flowing through a 60 watt light bulb running on 120 volts is 0.5 amperes. Power goes into heat, usually, or sometimes mechanical work, motors, radiated energy, lamps, transmitters, or stored energy, batteries, capacitors, inductors, managing the heat load in a complicated system, meaning a large computer, in which many kilowatts of electrical energy are converted to heat with the energetically insignificant byproduct of a few pages of computational results, can be a crucial part of the system design. Figure 1.2, a selection of common resistor types. Top row, left to right, wire mount ceramic power resistor, 20 watt vitreous enamel with leads, 20 watt with mounting studs, 30 watts vitreous enamel, 5 watts and 20 watts with mounting studs. Middle row, wire wound power resistors, 1 watt, 3 watt and 5 watt axial ceramic, 5 watts, 10 watts, 25 watts and 50 watts conduction cooled Dale type. Bottom row 2 watts, 1 watt, half watt, 1/4 watt, and 1/8 watt. Carbon composition. Surface mount thick film 2010 1206 0805 0603 and 0402 sizes. Surface mount resistors. Array 6, 8, and 10 pin single. Inline package arrays. Dual inline package array. The resistor at bottom is the ubiquitous RN55D. Half 1/4 watt, 1% metal film type. And the pair of resistors above the Victorine high resistance type. Glass 2 gigaohms. Ceramic 5 gigaohms. Soon, when we deal with periodically varying voltages and currents, we will have to generalize the simple equation P is VI to deal with average power, but it's correct as a statement of instantaneous power, just as it stands, incidentally. Don't call it current amperage. That's strictly Bush League. The same caution will apply to the term ohmage when we get to resistance in the next section. 1.2.2 Relationship between voltage and current resistors. This is a long and interesting story. It is the heart of electronics. Crudely speaking, the name of the game is to make and use gadgets that have interesting and useful I versus V characteristics. Resistors, I simply proportional to V. Capacitors, I proportional to the rate of change of V. Diodes, I flows in only one direction. Thermistors, temperature dependent resistor. Photoresistors, light dependent resistor. Strain gauges, strain dependent resistor, etc. All are examples. Perhaps more interesting still are 3-terminal devices, such as transistors, in which the current that can flow between a pair of terminals is controlled by the voltage applied to the third terminal. We will gradually get into some of these exotic devices. For now, we will start with the most mundane and most widely used circuit element, the resistor. Figure 1.3. What resistor? A. Resistance and resistors. It is an interesting fact that the current through a metallic conductor or other partially conducting material is proportional to the voltage across it. In the case of wire conductors used in circuits, we usually choose a thick enough gauge of wire so that these voltage drops will be negligible. This is by no means a universal law for all objects. For instance, the current through a neon bulb is a highly nonlinear function of the applied voltage. It is zero up to a critical voltage, at which point it rises dramatically. The same goes for a variety of interesting special devices, diodes, transistors, light bulbs, etc. If you are interested in understanding why metallic conductors behave this way, read chapter 4.4 to 4.5. A resistor is made out of some conducting stuff, carbon or tin metal or carbon film, or pole or wire, poor conductivity, with a wire or contacts at each end. It is characterized by its resistance. R is V/I. R is in ohms for V, in volts in I, and I in amps. This is known as Ohm's law. Typical resistors of the most frequently used type, metal oxide film, metal film or carbon film, come in values from 1 ohm to about 10 megaohms. 10 megaohms resistors are also characterized by how much power they can safely dissipate. The most commonly used ones are rated at 1/4 or 1/8 watt. Their physical size and by other parameters such as tolerance, accuracy, temperature coefficient, noise voltage coefficient, the extent to which R depends on applied V, stability with time, inductance, etc. See the box on resistors, chapter 1X and appendix C for further details. Chapter figure 1.2 shows a collection of resistors, with most of the available morphologies represented. Roughly speaking, the resistors are used to convert a voltage to a current and vice versa. This may sound awfully trite, but you will soon see what we mean.